What am I gonna do first? Yeah. We can do that. Yeah, okay, cool. Let me share screen. So that, let me give this some video. Did I do the other gun thing? Well, I did do the other gun. Hi.
Sorry, I just registered for
Cool.
class a couple of hours.
Welcome.
Is it?
Have a seat, yeah. I'm gonna run down because I did forget the attendance form sheet thing I need to sign, and I actually do need that, so. Over here. Hang out, talk to each other, say words. To know someone, say next to you. Make a friend. Put your name on there wherever you find it. It's vaguely alphabetical by last name, but like the columns are all on like, you'll figure it out. You can find your name, I'm sure. You're just out of the class that might not be on there. Write it in at the bottom somewhere. Ooh, oh yeah, what are you doing here? Not you, that's my email here. Yeah, go away. Let's open this up here. Those of you on Zoom, if you have questions or anything, you're also welcome to write things in the chat. Speaking of things in the chat, here's the attendance form that I would please like you to fill out. And myself, that. Are you not on? There we go. Many things. Cool. All right. That looks very bizarre. Let's get that fixed. All right, welcome. Good afternoon. Happy October 8th. What are we doing today? Let's see. What are we doing today? Good question. This is the afternoon class. There's so many things to talk about. Let's do a little bit more log, semi-log stuff. I have a couple non-computery examples where we can just do them by hand, and then I think one more like Google Sheets example, and then we'll try not to do any more of them unless we really feel like we need to. Where did I put those examples? There, right here. Cool. Let's go over here. So let's do the following example. Where'd you? One second. There's a bit of writing involved here, so bear with me. So here's example one. Suppose you are studying a population of squirrels on campus, because there's lots of them, over some period of time. When we plot our data, or when you plot your data, on a semi-log plot, you get a straight line with a slope of 0.25. Let's stop there for a second. There's more to write, but I just want to take a moment to say, if we know it's linear on a semi-log plot, then we absolutely know that the original relationship of the data was exponential or power function. That's not some of you saying it. It is definitely exponential. So semi-log corresponds to, I should say, being linear on a semi-log, but every time we do this, it's always linear on a whatever. It's linear on a semi-log or it's linear on the log, right? No one's ever giving you anything else. So if it's linear on a semi-log, we know semi-log goes with exponential, meaning something to the x power. If it's linear on a log, we know it's going to be power function, meaning x to a power. Okay, so we know it's going to end up being something to the x power at the end of the day. More right here. If the initial population of squirrels is 50, find a function, let's call it n of t, for the population at time t. All right, a lot of words. So here's what I would do. And there's lots of things you can do, but I would probably draw a little picture first. So here's my supposed semi-log graph. I know that for semi-log, the horizontal axis is just typical, meaning it's just whatever your variable is. In this case, I'm going to say it's t. And my vertical axis is log of my output. So it's not n of t in this case, but log of n, or log of n of t. I'm just going to write log of n. And then we are told that the graph has a slope of 0.25. That's a positive number. So something vaguely like this. And here's where things get a little bit, be careful. They didn't tell us the y-intercept. Well, they didn't tell us the y-intercept of the semi-log graph. If we were graphing it just regularly, where it looked exponential, then the y-intercept would be 50. But they told us that the number of squirrels is 50, but that's n. And on the vertical axis here, we have log of n. So this y-intercept, or vertical axis intercept, for lack of a better term, is t equal to 0 and n, or I should say the vertical value being log of 50 instead of just 50. Okay, so now we do the usual thing. We write the linear equation, and then we solve for y or n or whatever we're calling it, in this case n. So here's our linear equation. It's our quote unquote y thing, which is log of n, equal to our m times our x times our plus our b, or in this case, our m times our t plus our b value, which is log of 50. And I kind of like to write down, right? This is like our y equals m x plus b. The rest of this process should get fairly rote. Like it's the same steps over and over again. you're going to write everything as powers of 10 to undo the log base 10. Just going to rewrite this as 10 to the log of n equal to 10 to the 0.25t plus log of 50. On the left-hand side, we are always going to end up getting 10 to the log of n undoing each other, so you just get n, or whatever the letter is there. On the right-hand side, we always break this up as 10 to the first thing times 10 to the second thing. So it's going to be 10 to the 0.25t times 10 to the log of 50. We should simplify this as much as possible. What's 10 to the log of 50 equal to? Just 50. So we're going to rewrite this as n, or if you prefer, and I kind of do prefer, n of t equal to 50. We usually write the coefficient first, times, instead of writing this as 10 to the 0.25t, it's fairly typical to write it as 10 to the 0.25 to the t, to really, really emphasize the exponential relationship that is happening here. So that you have n of t equal to a constant times some base to a power to the t power. I did, that's what I just did. No. I can't do that because I don't have a logarithm in front of it. Right? We can't move powers down unless it's a log of something to a power. And then you can totally move the power down. So here I'm exploiting the rule that a power to a power, you would multiply the powers. So if you have powers multiplied, you can write them as a power to a power. I will say it's not really that different to write it this way versus if I had wanted to write it as n of t equal to 50 times 10 to the 0.25 times t, like that. That would also be acceptable. But again, we know it should be an exponential function. So we really like to write it as constant times base to the variable. Questions about this? All right, let's look at another one. It's a little bit different. Try to keep things on screen as well as I can while I still do more stuff. So here's another lots of words to read problem. Okay, so example number 2. In a case study of the biodiversity of trees, let's just say of trees, let's not write all the words, in a tropical rainforest, so in a rainforest, we don't need the word tropical there. The number of tree species, which we will call capital S, was plotted against the area in square meters. We call the area capital A in meters squared on a log plot. Log plot. So already we know we're eventually going to get something like y equals x to a power, or in this case, s equals a to a power. By the way, just some comments on word choice here. When I say that s was plotted against a, that means s is your vertical axis variable and a is your horizontal axis variable. Yeah. As is usual, a straight line is what we got because you're always getting a straight line when you do this. A straight line resulted with a slope of 0.84 and a vertical axis intercept of negative 0.06. Find the equation that relates. Relates number of species abundance to area. Again, while it's not super necessary to do so, I think drawing a picture here is useful. I'm going to draw a picture of the graph. And it doesn't have to be a good looking graph. It just has to be like a line that basically meets these characteristics, meaning the slope of the line should be positive and the vertical axis intercept should be negative. So, and even if we didn't get that right, it would still probably be fine. But here's a decent approximation of my line. Great. Where my slope is 0. Well, actually, before I write the slope, although there it is anyway, where my horizontal axis is log of A, and my vertical axis is log of S. Right? It's log, so we know that both axes are log of the variable, not just the variable itself. I should point out that we have slightly different information than we had last time. In the previous problem, they said at time equals 0, or the initial condition was that the number of squirrels was 50. And so we knew that we had to then find log of 50 as our actual vertical axis intercept. Here, they're not saying that. They're not saying when the area is 0, you get so many number of species. Also, that would be terrible. That wouldn't work actually, because if area was 0, what's log of 0? Undefined. So typically for these log ones, they actually can't give you like the initial condition. They can tell you just what the vertical axis intercept is. And that's kind of why they're giving it to you this way. So we don't have to do log of anything here. We're just going to say, hey, we know that this y-intercept, or I shouldn't say y, I should say vertical axis intercept, because it's not y on the vertical axis, it's log of s. But this vertical axis intercept is 0, negative 0.06. And once again, we have all the information we need to write the linear equation. I want you all to write the linear equation relating log of s to log of a. Should take you about 30 seconds. Do it. I don't see everyone writing things down. You should be writing things down right now. If you've got it and you want to start working on solving it, you can do that too. I should also just say, in general, for those of you that are newish or relatively new that haven't been to class before, if you have questions, you're welcome to ask them. If you need clarification on something I've written because it's hard to read or I've said it really fast, please ask. You're probably not the only ones like, what the heck is he talking about? Or what's the thing he wrote there that kind of looks like an 8 but might be a 5? So please, if something looks terrible or hard to read, just ask. I'm not offended. I'm happy to clarify. I know my writing is legible at best. Okay, so we're gonna do the same thing we did before. I'm gonna actually kind of start with just saying, we know we have like a y equal to m times x plus b. In this case, our y is the vertical axis thing, which is our log of s. I wish my s's looked less like 5s, but oh well. Our m is the slope, which is 0.84. Our x is the horizontal axis variable, which is log of a. And our b here is just negative 0.06. So instead of writing plus negative 0.06, let's just write minus 0.06. And then we're going to do the same. So I will point out, whether it's semi-log or log, after you've written this equation, the process for isolating your y thing is still the same. You're still going to write both sides as powers of 10, and then try to simplify as much as possible. So we're going to write this side as 10 to the log of s equal to 10 to the 0.84 times log of a minus 0.06. And then we simplify. 10 to the log of s is just s. We break up the right-hand side as 10 to the 10 to the 0.84 times log of a times 10 to the negative 0.06. Oops, I did not mean to press that button. Oh my God. Terrible. I've ruined it forever. I'm sorry. Oh my God. How many choices are there here? Can we get back to the normal day? Okay, that looks all right. Jeez. Oh, that doesn't look quite all right. Nope. Oh, there we go. Finally. I think that looks okay. Yeah, okay. I mean, okay. So I was trying to zoom in, not press extra buttons here, so you can see it a little bit better. We should definitely break this or simplify this a little bit more specifically. This power, so kind of the opposite of what someone was asked about before, about bringing the power down, we're going to bring this power up as the exponent of a in this logarithm, so that we can then rewrite this as s equal to, I'm going to put this part first, 10 to the negative 0.06 times 10 to the log of a to the 0.84. And just like 10 to the log of s is just s, 10 to the log of some stuff is just that stuff. So we can finally rewrite this as s as a function of area is equal to 10 to the negative 0.06 times a to the 0.84, which you really, for this one, you really should write it this way so that you can really see the power function relationship, that the output s is a function of a raised to a power, not something to the power of a. Cool. And then if you really want to, like, get out a calculator and get approximate values for 10 to the negative 0.06, but I would just leave it as is. So log, semi-log, that's interesting. I should ask, should we do another one like we did last week where we used Google Sheets to kind of make it happen? Okay, I see enough. Yes, cool. Good, because I like doing that. It's totally fun. So let me change something real quick here so that I can see what I'm doing without having to do this. Let me change my screen. Yeah, okay. Duplicate. Yeah, I know. Keep sharing everything. All right, yes, come on, all right. I'm way too zoomed in here. Okay, so I need to, sure. That's not what I wanted, Google Sheets. I want a new sheet. Yeah, sure. Actually, I'll just use, sure. I'm just gonna grab some data and go through it again. So here's the data I really want. Is this the one I want? Yeah. Cool. Nope, that's not the one I want. Sorry, I'm a liar. There it is. Cool. Yeah, don't look. Close your eyes real quick. Really fine. So this problem is from one of Tim Lewis's web work problems. In fact, we can even go look at it real quick. The only reason I picked him is because I was able to find those problems easily. So many things to choose from. Where are you, Tim? There you are. So let's go to the assignments real quick, just so you all can see the problem I was looking at. So I don't have to write it all down is really the reason we're doing it. Web work, I think it was web work homework 2. And if we go to problem, I want to say it was like somewhere down here. I think that's the right one. Yeah. So I grabbed this data. So let's read the problem. The following table is based on a functional relationship between x and y that is either exponential or a power function, meaning we don't even have to check if it's linear because they're saying it's not linear. You use an appropriate logarithmic transformation and graph to decide whether the table comes from a power function or an exponential function. So basically, graph it as a semi-log, meaning we're going to graph the log of y's versus the x's and see if that's the better linear function or linear fit. And then we're also going to plot log of y's versus log of x's. I feel like I'm saying the same thing. First, log of y's versus just x's, then log of y's versus log of x's. And see which one has the better fit, meaning which one has the better r squared value, the closer r squared value to 1. So let's go ahead and do that. Back to our sheet. So I'm going to paste my data here. Oh, and just so you all, if you're trying to do this like the fast way, if you copy and paste this, don't copy the x and y, because when I tried doing that before, it didn't work. If you copy everything but the x and y, and then try to just paste it over here, it should work. There we go. And then you do want labels, so I would encourage you to label this column as x and this column as y. And then we're going to want the log of x, or sorry, the log of y, apologies. So we want another x column, and then we want the same value. So this is just going to be equal to b2 And then just click on that little circle there and then drag it down to copy all the other things or to get the same equation, right? That's equal to B3, B4, B5, B6. And then for the Y ones, we want log of Y now. And we're going to then say that this is equal to, you need the equal symbol there, log of C2. And usually it'll just say, I want to do it for you and do the rest. So you can click there, or if you decide you want to do it yourself, you can then go back up here, click on the little circle when you see the, like, so the cursor changes into a plus, and then once you see that, you can click on it and drag it down to have it autofill the formula. And then we're also going to want log of X versus log of Y. Now, something I'll point out here. If we take log of X, what's log of 0? Fine. So that doesn't mean it's the wrong choice. It just means you have to ignore that data point. So if I was going to test the log of X versus log of Y, here's what I would do. I would still say this is log of X. I would still say this is log of Y. But then I would cut out the first one here. So it actually just, the easiest way to do this is to say that this is going to be equal to log of B3 instead of B2. And then it'll still do the same thing. If I click on this and drag it down, it'll give me log of B4, log of B5, log of B6. Same thing for the Y's. I'm going to say this is equal to log of C3. And then same deal. Cool. All right. So we've got all our data. Now we're going to test to see which one has the better linear fit. And since we're already over here, let's do this one first. So again, you just highlight all the stuff you want. You do, I would encourage you to also include the titles of the columns so that when your graph shows up, it's telling you what it's graphing or charting or tabling. Charting, we're charting. We're making a chart. So you insert a chart. And then it gives you your nice little chart. And then you do the following 7 things. It's not 7, it's like 3. You go to customize, go to series. You scroll down to the trend line. Then you scroll down a little bit further and you click on show R squared. And then you go back up a little bit and you click on the label and you change it to use equation. 2 things I want to point out. Thing 1, don't make the mistake of thinking this R squared is good enough. It's very close to 1, right? 0.981 is good. We'd be very happy with that in the real world if our best fit had an R squared of 0.981. But if it's not 1, then you should definitely check the other thing. Thing 2, and this is important, if this were the right choice, the equation they've written there is slightly wrong in that, for whatever reason, I don't know why Google Sheets does this, but the input variable they always just call X. So even though I've labeled my input column as log of X, they didn't write that there. They wrote just X. So if this was the right equation, I would need to write log of Y equal to 3.54 times log of X plus 0.833. So just be careful. If you're doing the log one, it should be log of Y and log of X, even though Google Sheets is not going to show it to you that way. Or if there's a way to make it happen, I don't know what it is. And it's not that important. You can just be aware. All right, so let's test the other relationship to see if it's a better fit. So we do the same process. We highlight the columns we want. We go to insert. We go down to chart. We go to customize. We go to series. Maybe I'll remember it next year when I have to do it again. But it took me forever to figure out what it was again, so I always forget. We go to trend line. We go to show R squared. Yay, it's 1. And then we go to label and use the equations. So there's the better fit. So the better fit is our semi-log graph because it's log of Y versus X. And I'm going to write down the equation real quick so then we can go ahead and find the relationship. Ooh, we can do that too. So our fit is log of Y equals 0.415 times X plus 1.24. Cool. All right. Let me do that. Yeah. Okay. So you can't see that. 1 second. Okay. So let's go ahead and do the thing. Why don't you all do the thing? Go ahead and find the equation. So solve for Y. And get something like y equal to some constant times some base raised to the x power. That's what your final result should look like. Your constant c and your constant b might look kind of janky, but they'll still be constants.
Also log of X or
No, it is not log. So yeah, good question. Let me actually go back and display that one more time. So since our best fit here, the one with the r squared equal to 1 was log of x versus y. Sorry, log of y versus x. Apologies for my misspeaking there. We know it's semi-log. If it had been this, if this one had the better r squared value, then it would have been log of y versus log of x. Log. But it's not, it's semi-log. All right, give it a try. Take this equation, write both sides as powers of 10, and solve for y. There's the work that I would do to simplify this and write it as y equal to some constant times some base to the x power. I would raise both sides to the powers of 10, so you have 10 to the log of y equal to 10 to the all that, 0.415x plus 1.24. The left-hand side becomes y. The right-hand side we break up using the additive law of x1. It says 10 to the this times 10 to the that. And then you could probably leave it like that, but you've seen me do it a couple times. My preference, and I think the general preference, is to write it as your constant first, and then this part rewritten instead of as 10 to the 0.415 times x, as 10 to the 0.415 raised to the x power. Something kind of neat is that you can actually go then graph the actual points on Desmos, is probably easier, and see that this function will fit exactly those points. And it will be exact because our r squared was equal to 1. In fact, let's go ahead and do it because I just think it's neat. It's also cool to see that things actually work. So Desmos, there we are. And I still have that copied, so hopefully it'll still paste. Yeah, great, awesome. So there's my points right there. Oh, we zoomed to fit your data. That's cool. That feels like a new feature, or just one I wasn't paying attention to earlier. And then we can go ahead and graph the function we just found. So we had y equal to 10 to the 1.24. Oops, I don't need to put. And then that's multiplied by, you don't really need the multiplication symbol there, but whatever. 10 to the 0.415. And then all of that raised to the x power. Perfect fit. It's kind of great. I mean, it's satisfying, right? You're like, yeah, it worked. Awesome. So that's how you know that your answer was actually right, because your function you just found fits the data perfectly. Awesome. Questions about this? Yeah. Here? Okay. We probably spent enough time well, enough time, as much time as I should spend talking about log and semi-log today. So let's continue on. There was, well, I should look at that real quick. Let me do this. Sorry. Always trying to change things around here. Let's change this to over there. Why you take forever? There we go. Okay, extend. Yes, great. Cool. Why every time that way? Why? Aren't you better at choosing? And it's obviously if you have to go somewhere to another class that or wherever you need to be, that is totally fine. I'm not just assuming I'm offending people and they're walking out. I was doing a thing. Yeah, okay. So sorry, one moment. There's one problem from Varn that I wanted to look at because people had asked about it. Not just one person, but multiple people. So let's go ahead and look there. Sorry, one moment. Yeah. Here we go. I believe it was number 27 from homework 1. So many problems. All right. So here's problem number 27. Well, you can barely see that. Oh, that's gigantic. So here's what we've got. We're starting with 850 bacteria and we double every 20 minutes. That's all we really need to know. Let's write that down. So let me show you what I write down actually, if I saw it. So starts with 850 bacteria, doubles every 20 minutes. Okay, cool. So at time equals 0, the number of bacteria, pick whatever function letter you like. N, Y, M, there's lots of choices. Typical are P, Y, N. I might say Y of 0 equals 850. Or better yet, I might make a table. Especially for these exponential growth or exponential decay problems, I really think a table of inputs and outputs is super useful. So I know that at time equals 0, the population is 850. And then I know that 20 minutes later, the population doubles. Now we have to decide what unit of time do we want to use. Do we want to use minutes? Do we want to use hours? Do we want to use days? Let's go back and read the question. So, well, based on the second question specifically, I think I want to do it in hours. Because the second question says, how many bacteria are there after T hours? So I want to write my function as a function of T, and I would like T to be in the thing I would need it to be in. So let's say that 20 minutes later, meaning 1/3 of an hour later, the population is going to double. So what is going on there? Okay. Sorry, brain. Sure. So 20 minutes equal to 1/3 of an hour, the population is going to double, and we're going to get 1,700. So now, let's talk about answering the first question, which is how many bacteria will there be after 2 hours? And the reason I'm doing this first before I do anything else is, well, you can answer this question without doing a whole lot of work. If I ask the question, how many bacteria are there going to be in 40 minutes, we would just double it and then double it again. Or 60 minutes, double it, double it, double it. Or 2 hours, which is just 6 doublings, we're going to double it 6 times. So, right, if we go to 2/3 of an hour, that's going to be another double. And then 3/3 of an hour, another double. And then 4/3, and then 5/3, and then 6/3. So we're going to double, double, double. So we have to multiply by 2, by 2, by 2, by 2, by 2. We're doubling how many times? How many 20-minute periods are in 2 hours? 6. So we're going to take our 850 and we're going to multiply it by 2 to the 6th power. Which is a number. I don't really care what the number is. This is the perfect. In fact, I shouldn't care what the number is because, especially if you're doing it in web work, you can write any unsimplified garbage you want to. Not that you would do that. No, I mean, I take that back. You should do that. You shouldn't worry about simplifying that. You should write it like that. And then let's see. I should preview just to make sure I didn't write something stupid. Always a good idea to preview. It never hurts to preview just to make sure your answer is written correctly. And then you can submit that. I guess I think it's too late to submit, right? Because it's like after the due date. If I check, oh, it's good. Right on. So if you're submitting things at web work and you don't want to simplify it or think, or just really gross to simplify, kind of nice. Let's look at the other two questions though, which were how many after T hours. So that's where we do need to do a bit more work. All right. So here's what we need. We need the model for exponential growth, which is always going to be something like y equal to c e to the k times t, or pick whichever constant letters you like. Sometimes people write c naught e to the kt, or p naught e to the at, or constant letter here, e to the constant letter there, times 2. Doesn't matter what letters you're using. And then we have to find c and k. C is also called C naught because it is the initial value or the amount of stuff you have at time equal to 0. If you know how much stuff there is at time equals 0, which we don't always know, but we often do know, you can just directly say C is going to be, in this case, 850. Or you can plug in the data and find it. If I plug in this data point, I'm going to plug in 850 for Y and 0 for T. K times 0 is 0, e to the 0 is 1, c times 1 is c. So I get 850 is equal to c. Finding k is a little bit more work. So to find k, we need to have one other data point. I'm going to pick the data point that's the next one, meaning when t is equal to 1/3, k is going to be, or sorry, not k, y is going to be double what it was. So using the second data point of t equal to 1/3 and y equal to 1700, I'm going to plug that in. I'm also going to use the value of c I just found to say that 1700 is equal to 850 times e to the k times 1/3. If you're doing a doubling time, this next step should always turn out the same. Divide both sides by the coefficient there and get 2 on the left. If you're doubling, it's always going to be a 2 there. If you're tripling, it would be a 3. So divide both sides by 850, you get 2 equal to e to the k times 1/3. We take the natural log of both sides to get natural log of 2 equal to the natural log of e to the k times 1/3. The natural log of e to the something is just the something. And then multiply both sides by 3 to get 3 natural log of 2 equal to k. So one way of finding the model, not the only way, is to say that y equals c, which is 850, times e to the 3 natural log of 2 times k, times t. Oh my God, terrible, terrible. However, it's not the only way of doing this. There's another equally valid way where you just kind of just talk it out to yourself. I know that sounds kind of silly, but like you just say, well, we're doubling every so often. So I know that my base should be 2. In 1 hour, how many times should I double? Yeah, show me on your fingers. 1 hour, how many doublings do we have? Right, 3. So I know that I should have 2 raised to the 3t hour. Let's think about this for a second. If t is 20 minutes, which is 1/3 of an hour, 3 times 1/3 is 1, 2 to the 1 is 2. So we're going to get 850 times 2, which will double it. If we plug in 40 minutes, which is 2/3 of an hour, 3 times 2/3 is 2, 2 squared is 4. We're going to double it twice. If we plug in 1 for t, which is 1 whole hour, which is 3 doublings, you're going to get 2 to the 3rd, which is 8, which is double, double, double. So this way of talking it out, all sorts of, you know what? This is the same as that. You could even right? Really, if you want to, you can write this as 8 to the t, because 2 to the 3t is 2 to the third to the t. You can totally write this as 850 times 8 to the t. And here, if you simplify this, this is 850 times e to the, bring that 3 up as the power. Be careful, James. Not just the 3 times t. You write this as e to the natural log of 2 to the 3t. And oh, look, the e to the natural log cancels, and you get exactly 850 times 2 to the 3t. So these really are the same thing, they're just written slightly different ways. I don't know how your professor talked about it. This first way of doing it is definitely how I usually think of it, because I did it that way first. Like I was like, oh yeah, and I was like, oh wait, there is this other way of doing it. So I want to make sure I covered both things here. Either way is fine, depending on what information you're given. This second way of doing it is less easy to do if you're not given nice information. Like if you're told that at time equals 0, the population is 600, and then 3 hours later, the population is 733. It's not a doubling time, so it's harder to kind of make this kind of thing happen. It's still possible, it's just weirder. All right. Should we answer the last question? Let's see what the last question is. So actually, let's talk. So the way you would enter this, you could enter either way. I would probably stick to my first way of doing it, right, as 850 times, I had e to the 3 natural log of 2 times t. So e to the, I need some parentheses, 3 times natural log of 2 times t. Let's preview that. Looks good. And then very easily, actually, that's how much we have after t hours. So if I want to find how much we have after 25 minutes, I'm just going to copy that. I'm going to paste it. I'm going to be smarter than I think I am and not just plug in 25, because it's not 25 hours, 25 minutes. You do 25 divided by 60. Works. And look how I didn't simplify any of that at all. Cool. All right. So there's an exponential growth. Good times. Questions about any of that? Time is it? What time? Okay, yeah. So I was like, do we end on the hour or on the half hour? On the half hour. Okay, cool. Still got a good 34 minutes here, right on. Lots of things to say. Trying to keep track of my papers here. Sorry, one sec. All right, so probably start talking about sequences. Probably start seeing what's on the paper. Okay, we're going to try to be efficient here with these sequences. Sequences. One way of writing a sequence is just as kind of a formula. So they might give you something like a sub n is equal to 2n over n plus 1. There's a formula for a sequence, and then we can be asked to say, write out the first 5 terms. So if I start writing them out, let's see if I plug in, and so I should say with a sequence, you're typically starting at n equal to 1, sometimes 0, but usually 1. And then you're just letting n increase to every subsequent integer. So for n equal to 1, I'm going to get 2 over 1 plus 1, which is 2 over 2, which is 1. And then for n equals 2, I'm going to get 2 times 2 over 2 plus 1, which is 3. Oh, there's something in the chat. I should look at the chat. Oh, sorry. Good. Thank you. Yeah. Sorry. Yes. If I keep going on and I don't see your chat saying you can't see what's on the screen, you can unmute yourself and say words so that I hear you, because sometimes I forget to see the chat. But yes, you're right. I totally forgot to share my screen again. Good call. Yeah. Let me do that. I was sharing the wrong screen. Apologies. There we go. Cool. Hope you can see now. So n equals 2, I got 4/3. You guys should have finished this by now. If n equals 3, I get 6 over 4, which is 3 halves. If n equals 4, I get 8 over 5. And if n equals 5, I get 10 over 6, which reduces to 5/3. Okay, so we can plug in numbers and get numbers out, and it tells us like this thing is doing something. But really what we usually care about with the sequence is what the sequence tends towards as n gets really large, or what the limiting behavior of the sequence is, or what the sequence might converge to? So does this sequence converge? And if it does, wow, can I write words? Does this sequence converge? If so, to what? Well, I should back up a second and say, well, what does it really mean to converge? If a sequence converges, it means that as you go further out to the right, as n gets larger and larger and larger, the values get closer and closer and closer to some specific real number. And I should say to one specific real number. If you get closer to two numbers, gotta be one and only one. So what we're really asking about here is, does the limit of this sequence exist as n gets infinitely large? So does this converge is really asking the question, what is the limit as n goes to infinity of this 2n over n plus 1? And we really can't just plug in infinity. Because if we did, what's 2 times infinity? Infinity. What's infinity plus 1? What's infinity divided by infinity? It could be anything, literally. So infinity divided by infinity, like 0 divided by 0, like lots of other things, is what's called an indeterminate form, meaning it can literally take on any value, or it can be undefined. So this could be 0, or it could be infinity, or it could be 5, or it could be 17, or it could be negative 27.2. Anything's an option. We have to do the work to figure out what it is. So really, when you see something, when you see a limit that's an infinity over 0 over 0, what that really means is do more work. That's what you should really see when you see something like this. If you see 0 over 0, doesn't mean you're done, doesn't mean you have an answer. It means I have to do something else to get a more specific result. So here, the usual kind of process is to, for a rational function like this, where you have positive integer powers of your variable over positive integer powers of your variable, is to divide everything by the highest power of your variable that is in the denominator. So I'm going to divide everything by n to the first. So we're going to say this is going to be the limit as n goes to infinity of 2n divided by n over n divided by n plus 1 divided by n. The step I'm kind of skipping a lot really is I'm multiplying the top and bottom both by 1 over n, which is totally allowed. I'm allowed to multiply the top and bottom by the same thing. It's totally valid. Just multiply by 1. And then we're going to simplify. We're going to write this as the limit as n goes to infinity of 2 over 1 plus 1 over n. Now we have to ask a very important question. As n gets infinitely large, what happens to 1 divided by n? Does it get big or does it get small? Well, if you had $1 and tried to divide it among 1,000 people, how much is everyone getting? A lot? A little. So 1 divided by a big number, or 5 divided by, right, if it was $5 divided by 1,000 people, everyone's still getting a little. Any constant divided by a big number eventually gets infinitesimally small. It gets closer and closer to 0. So this 1 over n, sorry, my nose is really itchy. So 1 over n goes to 0. So this limit is going to end up equaling 2 over 1 plus 0, which is 2. I should point out, this sequence never actually equals 2. Right? In fact, if you set it equal to 2, you wouldn't get a solution. If you set 2n over n plus 1 equal to 2, multiply both sides by n plus 1, you get 2n equal to 2 times n plus 1. You get 2n equal to 2n plus 2. Cancel, and you get 0 equal to 2, which is clearly a problem. Not true. But that's not the point. The point isn't that this is ever equal to 2. The point is that this gets really super duper close to 2. If you plug in, say, n equal to 1,000,000, then you plug that in, you get 2 times 1,000,000, which is 2 million. I know some fancy math there. Over 1,000,001. If you do that division, you get something like 1.999998. I think that's the right number of nines. I did it on my calculator earlier. Very close to 2, but not equal to 2. In fact, if you were to graph it, sure. If you were to graph it, Is that where my decimal is? No. Is that where it is? No. Did I close it? I get, oh, there it is. It's hiding from you. Put it up there. So if I were to graph it, I would probably not graph it as 2n over n plus 1. I'd probably graph it as y equal to 2x divided by x plus 1. And if I zoom in to the usual screen, you can see that, oh yeah, it certainly looks like y equals 2 is a horizontal asymptote. As you move further and further right, further and further right, this function gets closer and closer to 2. And even though it looks like they're just sitting on top of each other, eventually, if you zoom in enough, they're really not. You're getting really, I mean, really close, right? 1.96. So that's the idea here, is that if a limit, I should say, if a sequence converges, it means the limit gets closer and closer to, or I should say, it means the function gets closer and closer to some value, which means the limit exists. Okay. So let's talk some more about sequences converging. Yeah, let's look at another couple examples here. What about this sequence? B sub n equal to 3n over n squared plus 1. All right. I will admit freely, I don't find a lot of value in writing out terms. I think that's something everyone should be capable of doing. But if you wanted, I could do it one more time. B1 would be 3 over 1 plus 1. B2 would be 6 over 4 plus 1, which is 6 over 5. B3 should be 3 times 3 over 3 squared plus 1. But I don't feel like this is particularly useful because knowing what's happening with the first 5 or 50 terms usually isn't going to tell you what's going on. It might actually give you a false sense of what's going on. And be like, oh, it looks like it's getting bigger, and then eventually it actually gets smaller. So you certainly should do this if you're asked to do it, because you might get asked to do it. But just be aware that that's not really what we care about. What we care about is, does this converge? And so I guess I could have written in the previous one that a sub n converged to 2. I didn't write that, but it is true. So again, we're really just asking for the limit as n goes to infinity. And for sequences, it's always the limit as your index, typically n, goes to infinity. So we're asking, what's the limit as n goes to infinity of 3n divided by n squared plus 1? Same idea. What am I going to divide everything by this time? N squared, n cubed. Excuse me. It's going to be n squared. So let's divide everything by n squared and see what happens. You could skip this step of writing it out like this. I'm going to show it. But I feel like it'd be perfectly fine to jump to, I feel like something is flashing over here. Sorry, the chat, that's a 4 plus 1, not a 411. Yeah, good question there. There you go, the 4 plus 1, which equals 6/5. You can kind of skip this step and just go to the simplified version of saying it's the limit as n goes to infinity of 3 divided by n over 1 plus 1 divided by n squared. But you should show at least this step, even though you might know a shortcut for finding out what the limit is. And then 3 divided by n gets really, really small, and then gets big. 1 is 1. 1 divided by n squared also gets very small. So I get 0 divided by 1. Is that okay? Can you divide 0 by 1? Yeah, you can. 0 divided by any non-zero number is fine. It's when you divide by 0 that you're in trouble. So 5 divided by 0, 0 divided by 5, totally okay. Think about, in fact, if you really want to see it, just to make sure everyone's cool with that, 0 divided by 5, 5 goes into 0, 0 times, 0 times 5 is 0, subtract, your remainder is 0, we're good to go. On the other hand, oh my gosh, 5 divided by 0, how many times is 0 go into 5? I mean, 83? Sure, 83 times 0, I still have a 5, like, right? It doesn't work. Or not that it doesn't work, the answer could be anything. It could have been 83, could have been negative 83, could have been a billion. So dividing by 0 is a problem. There's something else I meant to say here. Oh, well, let's do the next one. Yeah. Oh, I know what it was. So we would say that this sequence, b sub n equal to 3n over n squared plus 1, converges to 0. But really, it's just as good to write that the limit is equal to 0, and everyone knows that that means that the sequence converges to 0. I know what I wanted to say. What I wanted to say was that we could have maybe reasonably guessed the limit was going to be 0 because the denominator is getting bigger faster than the numerator. Right? If you plug in a number like 1,000, the numerator is going to be 3,000, the denominator is going to be 1,000,001. And 3,000 divided by 1,000,001 is going to get small. And if you pick bigger numbers, the denominator is growing much, much faster because it's raised to a higher power than the numerator is going to. Okay. Let's look at another example. Yeah. Let's see here. Let me think for 1 second here. Let's say we have the limit. No, don't start with the limit, James. Jeez. Gotta write the sequence first. Sequence is a sub n equal to. I want something that's gonna like that. Yeah. So I just want to make sure that my answer is something that I want. Let's say it's 2n squared over 5 minus 3n. Yeah, cool. I like that. Okay. So here's where it's important to be extra super duper careful. If we do the wrong thing, we might end up in the answer that we're not sure about. Here's what I mean. I don't want to divide everything by n squared. It's not the highest power of n, it's the highest power in the denominator. Here's why. If I divide everything by n squared, so this is the wrong thing, don't write this down. It's not so much wrong, it's just it's not going to lead us to the easiest way to get there. We do this, and we divide everything by n squared, we get the limit as n goes to infinity of 2n squared divided by n squared divided by 5 over n squared minus 3n over n squared. We simplify. We get the limit as n goes to infinity of 2 over 5 over n squared minus 3 over n. And then as we let n get really, really big, what happens to 3 over n? Everybody. Thank you. How about 5 over n squared? Also 0. So what we have here is we have 2 divided by, it's not really 0, right? Those things aren't actually equal to 0, but they're very small numbers. You have 2 divided by a very small number. What happens when you divide by a very small number? Well, kind of the opposite thing that happens when you divide by a very large number. So when you divide by a big number, the result is, when you divide by a small number, the result is big. Here's what I'm thinking of. I'm thinking of like 2 divided by a super small number, like 1 over a million. Right? 1 over a million is very small. It's like 0.00000001. Probably I have one too many zeros. That's fine. But when you divide by a fraction, what do? You flip and multiply. So that's going to be the same as 2 times a million divided by 1, which is 2 million. So I just want to really, really, really emphasize here that when you divide by a very small number, the result is very big. Or, depending on the sign, very negatively big. And here's the problem with doing what we've done here. I don't know if that very small number is very small and slightly positive or very small and slightly negative. And that makes a really big difference in the answer. Writing it this way, I am unsure if my answer is that this thing is diverging towards positive infinity or diverging towards negative infinity. So the better, safer, correct thing to do is to divide everything by the highest power of n that's in the denominator. So if I do it that way and say the limit as n goes to infinity of 2n squared divided by n over 5 over n minus 3n over n, and then write this as the limit as n goes to infinity of 2n on top over 5 over n minus 3 on the bottom. Then when I start plugging things in, the 5 over n goes to 0. the 2n, well, the n does go to infinity, so this is going to go to infinity. So I get infinity divided by 0 minus 3, which is infinity divided by -3. And infinity divided by 3 is still infinity, right? But infinity divided by -3 changes the sign and gives us negative infinity. Which isn't super duper surprising. Like if you plugged in a big number here, if you plugged in, for example, 1,000 for n, a sub 1,000 would be 2 times 1,000 squared, which is 2 million, over 5 minus 3,000, which is negative 2,995. And that's definitely going to be a large number, but it's going to be a large negative number. So that's why I would really, really strongly suggest if you're evaluating limits like this, you definitely want to make sure you divide by the highest power of n in the denominator. The shorter answer to all, right? Yeah, the short answer to this long idea here is that if you have a rational function where the degree on top and the degree on the bottom happen to be the same, then the limit is the fraction of the leading coefficients, which is 2/1 here. If you have a sequence where the degree on top is smaller than the degree on the bottom, you're always going to get 0 because the denominator is growing faster than the numerator. And then if you have something like we just did where the degree on top is larger, you're going to get some sort of infinity as the result. Now, I should point out here, it would be correct to say that this limit does not exist. So I want to point out that a sub n equal to 2n squared over 5 minus 3n diverges. The limit as n goes to infinity of 2n squared over 5 minus 3n does not exist. However, we want to be more thoughtful and specific with our answer. And so it is better to say the limit is negative infinity. Because when we say that, what we actually mean is that the limit doesn't exist. And also this sequence gets really, really super negative. That's what you're saying when you say a limit is either infinity or negative infinity, is that the limit doesn't exist, one, it's not getting close to any specific real number. It's just either getting larger and larger and larger, or more negative, more negative, more negative. But we're being more informative about our answer. We're saying, oh, yes, I also know this thing, that this sequence happens to get super positively big or super negatively big. So even though it's correct to say this, it's more correct to say the limit as n goes to infinity of 2n squared over 5 minus 3n is negative infinity. You're still saying the limit doesn't exist. You're just saying how it doesn't. If that's a thing that's knowable. Let's look at another example. Let's say we have, a sub n equal to, how much time have I got here? Yeah, I got enough time. Okay. 6n squared plus 5n plus 1 over 3n squared plus 2n minus 1. Does this converge? What do you all think? Yay or nay? Converge or not converge? We see some thumbs. Thumbs up for converge, thumbs down for does not converge. And I think I'm seeing more convergence. It does converge, just like our first example. It's a limit of a rational function where the degree on top and the degree on the bottom are the same. The degree for both of them is 2, which is an unfortunate coincidence here. Because this sequence also converges to what value? Also 2, which is coming from the 6 divided by 3. If you did it the long way, you would see that the limit as n goes to infinity of 6n squared plus 5n plus 1 over 3n squared plus 2n minus 7. You could divide each term by n squared. I'm going to skip that step and just write the result divided by n squared. 6n squared divided by n squared is 6. 5n divided by n squared is 5 over n. 1 divided by n squared is 1 over n squared. 3n squared divided by n squared is 3. 2n divided by n squared is 2 over n. Minus 7 divided by n squared. And then everything that's divided by n or n to a higher power is going to get smaller and smaller and smaller as n gets larger and larger and larger. So all those lesser power terms become inconsequential, and the dominating terms, which are n squared in the numerator and the denominator, end up telling us that the limit's going to be 6 divided by 3, which is 2. So the shortcut that people often use here is that if you see that you have a rational function where the degree on top and the degree on the bottom are the same, then the limit ends up being the fraction of the coefficients of those highest power terms, but only if the degrees are the same. Any more minutes there? A couple more examples. So let's say our sequence looked like this. Yeah. 5n plus 1 over n minus 2 times -1 to the n plus 1 power. Oh, sorry, n plus 1, sorry. So if we start writing out terms here, let's see what we get. So if n equals 1, we get 5 times 1 plus 1, so 6, over 1 plus 2, which is 3, times -1 squared, which happens to be 2 times 1. If n equals 2, we get 10 plus 1, so 11, over 2 plus 2, times -1 to the 2 plus 1, which is -1 cubed, and -1 to an odd power is going to be -1. So this ends up being -11/4. If n equals 3, we're going to get 16 over 5 times -1 to the 4th. So positive 16/5. This is an example of what's called an alternating sequence. Every other term changes sign. Positive, negative, positive, negative. And the hallmark of this is typically -1 to the n plus 1 power or -1 to the n power. Or I suppose you could also have cosine of pi times n, because cosine of pi times n also changes from 1 to -1 every other time n increases. It's annoying, but it's true. So I'll just point out that you could also write this, again, kind of super annoyingly, as 5n plus 1 over n plus 2 times cosine of pi times n plus 1. Those are actually the same. I know they don't look exactly the same, but if n equals 1, 1 plus 1 is 2, 2 times pi is 2 pi, cosine of 2 pi is +1. If n equals 2, 2 plus 1 is 3, 3 times pi is 3 pi, cosine of 3 pi is -1, because you're over on the other side of the unit circle. So this is an equivalent but annoying way of writing that a function is, a sequence is alternating. Okay, so this is alternating, it's going back and forth. The next term would be, I don't know, 21 over 6 times -1 to the 5th, which would be a negative. Sorry, it's terrible looking. So here's the question. Does this converge? Well, half the terms are getting close to something positive. The odd numbered terms, 2, 16/5, whatever the next thing is. Well, if we take the limit of just the positive parts, the limit is n goes to infinity of 5n plus 1 over n plus 2. Show me on your fingers, what should that limit be? 5n to the first over 1 times n to the first plus 2. Thank you. Yes, that many. 5, right? Because we're getting a 5 over a 1 because we have the same highest power in the numerator and the denominator. But that's for that's for the odd numbered terms where you have a positive result. For the even numbered terms, all those are negative. So it's going to be the limit as n goes to infinity of -1 times 5n plus 1 over n plus 2, which is going to be -5. So every other term is getting closer to +5, and then every other term is getting closer to -5. And you know what a limit can't do? Is get close to 2 different numbers and exist. So since this limit is going in 2 different directions, right, it's kind of doing this deal here. It's going like here, say y equals, woo, wow, that's not very horizontal. So basically you have 2 and then further away and then further away, and both sides are getting close to their respective limit, getting closer and closer to 5, getting closer and closer to -5. But that means the limit doesn't exist because you aren't getting close to one specific number. So what we would say here is that the limit as n goes to infinity of 5n plus 1 over n plus 2 times negative 1 to the n plus 1 does not exist. And not in a going to infinity sort of way or going to negative infinity sort of way. It just doesn't exist. It keeps bouncing back and forth between two different things that are getting closer and closer to 5 and negative 5. And that's all we can really say. That limit doesn't exist. The only time that the limit of an alternating sequence exists is if that limit is 0. Because that's the only number that both a sequence of positive things can get close to and a sequence of negative things can get close to. Any other alternating sequence is going to diverge if it's not getting close to 0. So for example, this alternating sequence, negative 1 to the n times 5n over n squared plus 3, this will converge. And we know it converges because we know that the non-alternating part, 5n over n squared plus 3, is going to converge to 0. Because again, we can divide everything by n squared and get 5 over n over 1 plus 3 over n squared. That goes to 0. That goes to 0. So we're left with 0 over 1 plus 0, which is 0. So you've got some positive terms getting closer and closer to 0. And then you've got the every other negative term also getting closer and closer to 0. So we are getting closer and closer to the same single value, which is 0. So it is correct to say here that the limit as n goes to infinity of negative 1 to the n times 5n over n squared plus 3 is 0. So basically, if you're trying to see if an alternating sequence converges, you look at the non-alternating parts. You ignore the negative 1 to the n or the negative 1 to the n plus 1. You ask yourself, is the limit of that 0 or is it something else? If it's 0, you're good, it converges. Not 0, it doesn't. Still good. Times it. Okay. One more thing. I'll say one more thing. So all the sequences I mentioned so far are examples of sequences where you have the explicit formula for the sequence. But there's also these things called recursive sequences. Like, where'd you go? Where's my example here? Right, 1 second. Hiding from me. Oh, that one's terrible. Not that one. Do this one first. So we have something like a sub n plus 1 equals 1/2 times a sub n plus 5. And we are given that the first term is equal to 4. So this is a recursive sequence, meaning that to get some term, you have to know the previous term. So in all of our other examples, I was able to be like, well, the millionth term is you just plug in a million and you get 2 million over 1,000,001. I couldn't do that here. I couldn't just plug in a million. I have to first know the previous 999,999 terms to be able to figure out what the millionth term was, if I couldn't figure out what the explicit formula was. So let's go ahead and start finding some terms. So we know that the first term is 4, and they have to give you the first term for a recursive sequence. Someone has to tell you where to start. So here's our starting place. And then a sub 2, I'm subbing in 1 for n. A sub 2 is going to be 1/2 times a sub 1 plus 5, right? I'm letting n equal 1. And I'm going to get 1/2 times, well, a sub 1 is 4. We have 1/2 times 4 plus 5, which is 1/2 times 9, which is 4.5. Let's do that a couple more times. A sub 3 is going to be 1/2 times a sub 2 plus 5. Right, it's always the next thing is some function of the previous thing. That's going to be 1/2 times 4.5 plus 5. Right, we're just plugging in this number here. And then we're going to get 1/2 times 9.5, which is 4.75. And then we'll do it one more time. Let n equal 3. If n is 3, we get a sub 4 over here. We get 1/2 times a sub 3 plus 5, which is 1/2 times 4.75 plus 5. And 1/2 of 9.75 is 4.875. It kind of looks like we're getting closer and closer to 5. And we are. And if you think about it, I'm plugging in a number less than 5. I'm adding it to 5, which is going to be a number that's a little bit less than 10. And then 1/2 of a number less than 10 is still a little bit less than 5. So every time I do this, I'm going to get closer to 5, but still less than 5. So is 5 the limit? Well, to know if something's the limit of a recursive sequence like this, we have to find the fixed points with the equilibria of the sequence. Here's how we do that. So a fixed point is something you plug in and get the same thing back. So here's how we find them. We want to be able to plug in some number. We usually call it L, capital L for the limiting value. We want to plug L into the sequence and get back the same value for the next value. So we just basically replace every A sub whatever with L and then solve for L. So we're going to multiply both sides by 2. We're going to subtract L from both sides. Oh yeah, L is 5. And look, if you plug in 5, right, if A sub n is equal to 5, then A sub n plus 1 is going to be 1/2 times 5 plus 5, which is 5. So if you put 5 in, you get 5 out, which means it's a fixed point, also called an equilibrium. Things aren't changing, right? That's why it's called an equilibrium, because it's the place where things aren't changing. So 5 is the only candidate for the limit, and it certainly seems like based on where we started that we're getting closer to 5. So it would be reasonable to say here, yeah, we're pretty sure that the limit as n goes to infinity of this sequence is in fact 5. Next time we'll see that there are some other recursive sequences that have multiple options for the fixed point, like there's more than one fixed point, and then we'll have to pick the right one based on the behavior of the sequence, or we'll have to observe that neither of them are right based on the behavior of the sequence. All right, 3:30. I will stop talking. Have a lovely rest of your day. Hello. Sure.